Hey guys, we made it. This is it. The last review video before the AP exam. Today's review is on differential equations. We're going to talk about solving initial value problems, separation of variables, exponential growth, and those famous slope fields. Shouldn't be too bad. We'll get through this. At the end, there's a free response question for homework and some optional multiple choice if you want. We got this. All right. First up is initial value problems. Initial value problems are just a problem that gives you some kind of differential equation like this. dy dx is 3x squared plus 4x minus 5. And then they give you some initial value like, hey, by the way, there's an initial value of y of 2. When you plug 2 in, you get a negative 1 out. So you can use that initial value to find the equation for y, and then it'll typically ask you to find something like y of 3. Sometimes they're word problems. Sometimes they're written like this. Either way, the basic format's the same. You got this differential equation. You're trying to find y, so that means you need to find the antiderivative. Don't forget you need to add that plus c because there's an infinite number of antiderivatives, all plus some constant. That's the whole point of this initial value. You can use the initial condition to figure out what the constant is. Because I know when I plug a 2 in for the x, I get a negative 1 out for the y. So put in a negative 1 for the y, put in 2's for all the x's, you can figure out what your c is. Don't stop there. That's the biggest mistake students make with initial value problems. They're like, hey, I found my C. Like you're normally asked to do something with that C, right? So here's the original equation with the correct C, right? There's my antiderivative, same thing, but now with a C of negative 7. And then the question asks me to find y of 3, which means what is y when you plug an x value of 3 in? So then do that. Y of 3 is just plugging a 3 in there. In this case is 23. That's basically it for initial value problems. You're given a derivative, you want to find the original equation. Usually you have to do something with that original equation, like finding y of 3. Sometimes you have to use something called separation of variables to solve a differential equation. Because a lot of times the derivative they'll give you will look like this. dy dx equals xy squared, right? So this one problem is saying solve the differential equation dy dx equals xy squared given that y equals 1 when x equals 2. So there's another initial condition. This is just another one of those problems like the last time, except this time like I gotta find the antiderivative of this, which is tough because it's got a y in it. Anytime you're asked to find the antiderivative with a y in it, separation of variables is going to be your thing. You want to get the y's by themselves, the x's by themselves, and then you do it. So we get the y over here by putting 1, multiplying both sides by 1 over y squared with the dy. Get that dx on the other side, because then I've got dx, and then I've got all my y stuff together and all my x stuff together. Then you can integrate, right? I'm going to integrate both sides. If this stuff equals that stuff, the integral of this will equal the integral of that. Integral of y to the negative 2 is y to the negative 1, negative y to the negative 1. Integral of x dx would be 1/2 x squared plus c. Yes, technically I could have put a plus c on this side, but I like having the plus c over here. Just having that one constant take care of the constant for both of these. We've talked about that in the past. A couple things I glossed over here that I kind of want to talk about. The 1 over y squared, you'll notice I changed it to y to the negative 2 before I took the integral. That's because this format tends to be a lot easier to find the antiderivative in. We've talked about this before, where if you're finding derivatives or antiderivatives, having it in exponential form tends to make the calculus a lot easier. Having it in fractional form tends to make the algebra a lot easier. So you really want to be able to shift between those pretty freely. All right, so this is where I was at. I've got negative y to the negative 1 equals 1/2 x squared plus c. I got to figure out that c. That's what this initial condition is for. So you can just plug in I'll plug in a 1 for the y, right? Plug in a 2 for the x, and then I can just solve that and figure out my c. In this case, c was a negative 3. So I could rewrite my equation. It's going to look like that. Same thing as I found before, just now with a 3. The one thing with this equation is it's kind of weird. It's not a nice y equals equation, and normally that's how I want my equations if that's possible. And in this case, it is. It's not a problem. I can rewrite this like that. It's just tough check to make sure we understand what we did. I didn't like the y down here in the denominator, so multiply by y. That'll get it over here. I didn't like this stuff over here, so I divided it. That's why that got here. right? So then I got a nice y equals equation. It doesn't look super nice right now. One real quick thing I could do to fix that is multiply by 2/2. That'll get rid of that fraction within a fraction, right? So timesing the top by 2 gets you -2. Timesing the denominator by 2 gets you x squared minus 6. There is my solution, right? Why I found that what my y was equal to. This problem didn't go on and ask me to do any more with that. It just said solve the differential equation. Solve the differential equation just means, hey, figure out what y is equal to. Most of the time, like I said, most of the time that's how things like this, like find the value of y when x equals, let's say 0. Like that's most of the time the types of initial value problems we'll see. And then if it did that, then it's just one more step. Put a 0 into there, see what you get out for y. In this case, it looks like it'd be 1/3, right? All right, we're moving. Nice. Exponential growth. Exponential growth. There's an important memorization. Again, that's kind of nice about this year. You could have this on a quick reference sheet, which, yes, I'm still working on. I'll try to get that for you. The solution to all differential equations of the form dy dt equals ky look like y equals some initial starting amount times e to the kt. All right. So we talked about this when we first started talking about differential equations. Basically, it was saying that if you've got a derivative that equals some constant times y, this is saying that the rate of change of y depends on how big y is, right? This is one of those ones like half-life or population growth, where how quickly something is growing depends on how big the population is, right? If I've got a small town of population 20, right, growing by half a person per year is a pretty big rate of growth. But if I had a population of 10,000, half a person per year is really small. So when you do this, when you solve this, it always will end up looking like that. In this case, where let's see if I can get a pen up here quick. Where that A is your initial starting amount. That's like your initial population or whatever you're measuring. That'd be the initial amount. Don't know why I'm typing with mouth, but with a mouse. But I'm just about done. So that's the initial amount. And T stands for time, right? And that K, that's the same K as this one, same K. And that's called your growth rate. That's how fast you're growing or shrinking, right? So any of these problems, anything that has that kind of derivative has this type of solution. I could go about solving this by separation of variables that involves a natural log. We did it. It's not too hard. In fact, I would recommend trying to solve this one as if it was just initial value problem, and you'll see you'll end up with y equals some constant times e to the kt. It's just, in this case, we rename that constant a because it ends up being your initial amount, and it works out slick. Knowing this saves you a whole lot of time on an AP exam, right? Instead of actually working it out, you can say, hey, I already know the solution. It's going to look like that. So an example of using the differential equation dy dt equals kt. This one says solve the differential equation dy dt equals 3t for the point 0.05. Since it looks like this, yes, I could use separation of variables to solve that, but that's one I know already. That one's going to look something like this. Y equals some initial amount times e to the kt. In fact, this one was super nice for you because they gave you the initial amount, right? In this case, at time t equals 0, I've got a value of 5. So I know y equals 5 times e to the 3t. Oops. 3 because that's my value of k. Done. Like it's a 2-second problem. If they wanted to, they could have made this slightly harder. They could have said, instead of for the 0.05, for given, let's say they say it this way this time, given that y equals 8 when t equals 2. Sure. If that happened, then I'd still know it looks like this because it's still a dy dt equals some k times t. So I know my answer would look like this. But this time, when I see it, they didn't give me the a. They didn't give me the initial value. All they gave me is that k is 3. So I'd know this would be a 3t. And I'd know my equation would look like that. But my initial value, that happens when time t equals 0. They gave me time t equals 2. No problem, still easy to fix it. I can take this and I just plug a 2 in for my t. And I know when I plug a 2 in for my t, I get an 8 out for my y. And then I can say, oh, now that I can see that, it looks like 8's going to equal whatever that initial amount is times e to the 6th. And I want to get rid of that e to the 6th. So divide by e to the 6th. It looks like my initial amount is whatever 8 divided by e to the 6th is. And then you could write that usually in decimal form as your answer. Or if you really wanted, you could leave it as a fraction. You say, hey, that initial amount, that was 8 divided by e to the 6th. Sure, e to the 6th. And then that would be my final answer. Whatever that's just some number, right? Slope fields is the last one. So with slope fields, we know slope fields look something like this. They give you a differential equation and they might ask you to sketch a slope field. So for an example for this one, I want to find slopes of all these points. So there's a lot of points I got to sketch. I made my work hard for myself. I'll just give an introduction for how we're going to do this. So I know the slopes, dy dt, or sorry, dy dx, the slopes are always going to be the y value divided by the x value, right? That's all my slopes. So if I can make my life easy, I can think of these different values. Like for instance, if y was 0, like y is 0 here and here, sorry, y is 0 here and here and here, all these ones. If y is 0, I'm going to have 0 divided by something. That's a slope of 0. So I'm going to have a slope of 0 here, slope of 0 there, slope of 0 there. All along this y-axis, it's going to have a slope of 0. Except at this one. You'll notice I skipped that one because that's when I'm dividing by 0. 0 divided by 0 is not 0. 0 divided by 0 is undefined. So I'm going to have an undefined slope for all of these ones here. Since the slope is undefined, I'm just not going to write it. I don't know what's there. Could be a corner. More likely it's going to be a vertical slope, but it's undefined, so I'm not going to put anything there. Going on, let's see here. If I had a y value of 1, well, I'll put a 1 in here. So 1 divided by 1, that'd be a slope of 1. Then 1 divided by 2, right? That's a 0.1 comma 2 would be a little slope of 1/2. Then 1 divided by 3, slope of 1/3. Looks like it's getting just flatter and flatter and flatter. Same thing if I put a 2 in here, 2 divided by 1 is 2, that's going to have a slope of 2. 3 divided by 1 is 3, slope of 3 is getting steeper like that, right? This looks like a handy one, right? This one was 1 divided by 1. That's 2 divided by 2. That's still a slope of 1. That's 3 divided by 3. So you can make yourself life a lot faster if you notice some patterns. Like, right, this whole line, that's going to definitely be the same slope all the way, right? Anything divided by itself is 1. Same thing here. That's 1 divided by -1. That's -1. 2 divided by -2 is -1 as well. All these slopes are going to be -1s. I know that's going to look like that. There's a lot of symmetry show up in slope fields. As I go this way, the slopes get less and less steep, right? So I can do that, which means as I go this way, they get more steep, right? It's going to look something like that. I can check that on this side too, right? That's a -1 for my x. So this is when y, that's a -1 slope. Then y value of 2, that'd be -2, -3, -4. It looks like it's going to be the same type of thing as before. Less and less steep as I go this way. And it should be some kind of mirror image of the other side. All right. I could keep going, but I can, looking at this, I can guarantee it's going to look like just be a reflection of this, right? Less and less steep this way too. And we could sketch that whole thing out. Less, roughly. More steep going this way. More steep. More steep. All right, whatever. It's going to look something like that. And I could finish that out, but I won't. So that's sketching a slope field. I've got one thing hidden here. I want to see what it is. It looks like we got a question. This says, given an initial value of 1, 1, for what domain is your solution valid? All right, so a lot of times slope field might ask you to sketch the solution curve for a given point. So for instance, for this one, if I had a point 1, 1, the solution curve would just follow along that line, right? Follow that line, follow that line. It looks like it keeps going. I'm undefined there though, and then it keeps going this way. And with slope fields, if you're ever undefined, you can't be like, oh, I pick it up right here because maybe it was a jump discontinuity and you actually picked it up down there. So if I was to do this one, my solution follows this right up to the point where I was undefined. So my solution would be valid for everything from 0 on to infinity, not including 0. If you wanted another example of a curve, I could pick a different point. If I said, instead of 1, 1, what if we picked, let's say, well, let's make one a little bit different. Let's say 1, 2. If I started here. If I started here, I can see, well, that's got a slope of 2. It's going this way. But then as I go this way, that looks like a slope. This looks like it's curving upward away from the line, so it's getting steeper. And then as I get away from that line, it looks like it's getting steeper and steeper. So it's going to look rough. I don't know, roughly like that. This isn't a great one for doing it. But essentially, you're just following what those curves look like. So like if I look here, it looks like these lines are getting closer and closer. So it looks like I might have some kind of asymptote here, but it'd go further outward. And same thing for that side, right? So if you're given some initial value, you kind of want to follow those curves and see what you're going towards. Yeah, this isn't a great one for doing that. I wish I picked a better one. My apologies that it didn't work out great. Normally it'll work out much better. Like if you had someone that it'd be like some kind of curves like this, right? If this was my slope field, just sketch this out quick. If this was my slope field and I had a point right there, like the solution curve would definitely be this circle because that's what's following the slope curve. Although it would only be valid until this slope got undefined. But that's how slope curves work. And just follow those slopes until you see what type of shape your graph looks like. All right, that is it. Today we have an assignment, the 2018 free response question number 6. Give it a shot. I think it has some slope fields, which would be good practice for you, especially since I wasn't especially happy with this example. It'd be a good one for you to see. There is an answer key, so you write along with it so you can check your answers. For some additional practice, there's a couple of these right here from the 1998 exam. That's optional, but it might be a good one to hit, especially it's a good one for exponential growth. Good luck. I'll talk to you later.